Good morning, good morning, good morning, my dear lovely warriors. For the one last time, you will be meeting me before your physics board examination, where it's expected that around 30 lakh plus students will be writing it. But the good part is, here the ranking does not matter, and most of us are writing it just for the sake of eligibility because we want to get into the top notch best colleges in the country, and we want to clear this mind block or this roadblock, which is just mere a certificate for all of us. But let me tell you, it's more than that. The studies which you are doing for your boards definitely helps in your other competitive examinations. You might not realize this in particularly in your January attempt, because most of the students do not study so much for boards or become serious for your board examinations after January attempt. And that's when you realize that your April attempt went much better, because not just you have gained that experience in January, but also because you have been preparing for the 12th standard syllabus more rigorously, in depth, going through the NCERT lines. And although you might feel that you have wasted entirely your time for the boards, but actually indirectly you have been preparing for your second attempt. So you will find a lot of difference, especially the 12th standard syllabus. The 11th standard syllabus is what you need to take care of. We'll be doing all of that on this Vedantu J English channel. So you need to stay tuned, stay subscribed, and yes, do not forget to smash the like button. This is your Captain Shreyas. Good morning, happy morning, Krishna. Nice to see you. Unknown, Meka, Aditi, welcome. All the warrior pandus, MG Vlogger, Tiger, good morning. Yes. So let's begin. Let's begin. Yes. Thank you for liking. Thank you for subscribing, guys. So I will start giving you formulas. We'll start revising all the formulas one by one. Starting off with the first chapter, guys. I will just make a quick block diagram so that you guys can quickly revise with me. We'll try to keep the session for an hour, not more than that. Okay. So for the first thing, there are four things which I want you to remember. Force is equal to, which we are talking about electric charges and that. So electric force is equal to Coulomb constant, charge 1, charge 2 divided by R square. Then your electric field is K Q by R square. Just like force, you have potential energy which goes like K Q1 Q2 divided by R, and you have your potential which is just given by K Q divided by R. The unit of this, just like this one is Newton, this is nothing but Newton per Coulomb. Newton per Coulomb. This is joules. This is joules per Coulomb. You can go from here to here. You can go from here to here by saying, if I find the force per unit test charge, where that second ways, where that charge tends to 0, where that test charge tends to 0, the force per unit test charge will give me the electric field. Okay, same thing over here. If I go from here to here, basically you are nothing but trying to find the potential energy per unit test charge, where the test charge is becoming 0. And you can go from here to here. You can go from here to here. You can find the force. If you multiply the charge with the electric field, you can also go from here to here. You can find the potential energy if you multiply the charge with the potential. You have seen all these formulas even before. And because U is Q delta V, U is Q delta V, you can also say delta U is charge into potential difference. This change in potential energy is the work done by the external forces, but also keep in mind this is negative of the work done by the electric forces. Negative of the work done by the electric forces. These formulas are very, very useful, my dear students. Similarly, when you want to find from force the potential energy, the logic goes like this, where you find the potential energy defined like this. It is integration of force with respect to displacement, integration of force with respect to displacement from infinity to r, but it is basically the work done by the external force, in bringing the charge from infinity to that particular point. So it is work done by that external force. This force is usually the electric force, so that is why you put a minus sign over here. So that is how it comes out to be. U is minus FDR from infinity to R. And same way, electric potential we can find out from electric field like this. You just take integration of the work done, basically Q E is the force into dr from infinity to r, the whole thing divided by the charge. The work done to bring a charge from infinity to that particular point. So you put a minus sign also, that is very important. Per unit charge is going to give you the potential, is basically going to give you the potential. The reverse, if you have to go, if you want to find the field, then it is nothing but minus dv by dr. It is minus dv by dr. Here, if you want to go the reverse, it is force is equal to minus du by dr. Yes, all these formulas you must be able to recollect. Potential energy is the work done by external force from infinity to r. Potential is the work done per unit charge. As you can see over here clearly, this q and this q eventually gets cancelled. Is this clear, everyone? Everybody remembers this? Are you able to recollect this? Yep. This is a very beautiful, simple mind map for all of you. Okay. Next, let's go to the next mind map. Over here, you don't need anything else. Apart from that, you should know the properties of charge, the properties, the properties, the properties of charges, like it is a scalar quantity, then it can be added, and subtracted with algebra, simple algebra. Then the total charges are basically conserved. Total charges are basically conserved. Also, it is quantized. Meaning the total charge is always n times of E. N is always an integer. E is nothing but 1.6 10 to the power minus 19 coulomb. 1.6 10 to the power minus 19 coulomb. All these things you should know. Next, if you take an electrical dipole, whose value is given by charge into the separation, which is basically 2L, it always goes from minus to positive. Don't get confused. It is not from positive to negative. Keep that in mind. So the electric field will probably go like this, like this. Also, some of the electric field lines will come like that. Yep, it will go like this. Like this. Yep. So this particular position is called as the equatorial position. This is called as the equator. This one over here, this is called as the axis. When you try to find at any point on the axis what is the field, the electric field on the axis is given by K, dipole moment, but you multiply it 2 times. So it is 2 times Kp divided by the distance cube. 2 times Kp divided by distance cube. Over here, when you try to find the electric field on the equator, it is just Kp divided by r cube. There is no 2 over there. The field on the equator is always going to be less. If you try to find any general point, the value, let's say this is theta, the value of the electric field at any general theta, it will be given by Kp divided by r cube. Here you have 3 cos square theta plus 1. That is the formula for in general point making an angle theta with the dipole moment. Similarly, you have the formula for potential also at any general theta. It is just Kp cos theta divided by r square, not r, it is r square. That is something which you should remember. So on the equator, the potential on the equator, if you put the formula, theta will be 90 degree. So the potential is always going to be 0. It's an equipotential line. Here, this side you get positive potentials and this side you get negative potentials, my dear students. I hope this is absolutely clear. Okay. And the dipole moment has a unit of coulomb into meter. It is not centimeter, it is coulomb into meter. That's another formula which you should know. Next formula, my dear students, everybody remembering this? Yeah. Uh, Sir, minus sign, is it needed? Okay. See, I'll tell you one thing. When you are going on the equator, this is the magnitude. Direction wise, dipole moment is here, field is this side. So you can use that minus sign if you're using it in vector form. Otherwise, the magnitude is understood. But direction wise, yes, the equatorial field is opposite. So this electric field in vector form on that equator will be minus k p bar by r cube. And this in vector form, electric field on the axis will be positive only. It is in the same direction as that of the dipole moment. So if that is in the vector form, otherwise you don't need it. Okay, I hope this is clear. We generally write the magnitude just like we know spring force is kx, direction we automatically show it in the diagram. But yeah, if vector form is needed, then show it with that negative sign. Okay, next important thing, my dear students, is that if you have a wire which is charged and lambda is nothing but how many coulombs of charge is there per unit meter, then at a distance of r from it, you will get the value of electric field using Gauss's law, which is just given by 1 by 2 pi epsilon naught. Here you have lambda and divided by r. This is due to a long wire. Yes, you should also know Gauss's law, my dear students, which is nothing but the cyclic integral of electric field with the area is nothing but how much charge totally is there inside divided by epsilon naught. This particular quantity is called as electric flux. This particular quantity is just called as electric flux for a closed surface, for that particular closed surface. Using that only you will get this. The next particular thing which you should know is if you have a charged sheet, and you know that the electric field lines are going this way as well as this way, and what you know for the charge sheet is sigma. Sigma is how many coulomb of charge is there per meter square, charge per unit area charge density. This particular electric field, because it is going both ways, both is 2, so 2 epsilon naught. Sigma is charge per unit area. But if the same thing happens for the surface of a conductor, this is the charge on the surface of a conductor. So the behind part is probably inside the solid, because of which you will see inside of it, the electric field is 0. So the field only comes on this side. Then the electric field is just given by sigma by epsilon. One number is there because field is going only on one side. One side means 1, both sides means 2. That is something which you should keep in mind. Is that absolutely clear? Very good. Then the next formula, my dear students, is this one of a solid charged sphere uniformly charged sphere versus a shell. So if you have the charges only on the surface versus the charges even inside that thing. So this is basically for a shell or a conductor. A shell or a conductor, because on a conductor the charges are only on the surface. This is a uniformly charged sphere. This particular sphere 100% has to be insulating in nature or non-conducting. Insulating in nature or non-conducting, because if it was a conductor, the charges would repel and it would come on the surface. Okay. Every time the radius is r, charge is q. So what is the value of the field when you are outside versus inside? If you are at a distance r, if you are at a distance r outside, the field is very simple. If you are at a distance r outside, that field is very simple. You treat the charge like a point charge. It is just kq divided by r square. Same thing, you treat it like a point charge. The electric field is kq divided by r square. The problem happens when you are inside over here. So the moment you are inside this particular field, shell, anywhere you go inside, it is always going to be zero. Yes, no matter where you go, inside a shell, the field is going to be zero. But the same thing over here, when you are inside, at this particular distance r, the electric field is given by kq divided by the radius q multiplied by small r. That is very important. This radius that I'm talking about is the radius of that particular sphere. So r cube is there, keep that in mind. R cube is there, yep. And here you have that small r, which is the distance from the center. When you talk about the potential, although over here potential at this point is just kq by r, just like a point charge. But the moment you are inside over here, the potential is kq divided by radius, which is going to be a constant. But this radius is the radius of that conductor. R will not be variable. It is a constant. It is just going to be the same everywhere. Yeah, keep this in mind. These formulas will help you plot the graph as well. Yes, these formulas will also help you with the graphs as well. Okay, great. So these are some formulas which you should definitely know, my dear students. Uh, so if you just see your NCERT also, these things are there or automatically. All these things, dipoles and everything, flux concepts. Yep. Uh, Now we'll also go to dipole in a field and all of that. Okay. Yeah, all these things are there for shells and spheres. So the last thing is dipoles in a field and their potential energy interaction. That comes in the next chapter. That basically comes in chapter number 2, where you see the potential energy formulas, which we are just seen right now, and yes, all these formulas we have seen, potential energy in an external field, etc. Okay, so we'll just come to that particular formulas, guys. See, guys, most of the times you will be using these formulas, so please be very careful with the sign convention is what I would say, or else you will make big blunders. Okay, be very careful. So what about when you take a dipole inside an external field? So I'll just do it over here. Imagine you have a dipole like this. This is minus, this is positive, and it is placed in somebody else's field. This is external field, not the dipole's own field. Not the dipole's own field, because the own field will look like this. Axial, equatorial positions, we have already figured it out. And let's say the angle made over here is theta. Then the dipole will experience a torque to bring it back in the direction of the field. That torque vectorially is given by the dipole moment crossed with the electric field. But if you want it with the magnitude, it will be E sine theta, and you have P over here. And of course, That is the magnitude of the torque. It is PE sine theta. Same way, you can also find the potential energy of the dipole. The potential energy of the dipole, if you talk about with the vector formula, it is nothing but minus p vector, p vector dot e vector. But if you write it in the magnitude form, dot will be replaced by cos. So it will be nothing but pe cos theta. It will be replaced with pe cos theta. The three peculiar positions of this dipole which you should know: once when it is aligned, once when it is 90 degree, and once when it is opposite to the field. So when it is aligned, that means theta is 0 degree, here theta is 90 degree, and here theta is 180 degree, guys. So in these cases, you will see that the torque is 0 when theta is 0 or 180. Torque is 0. But here the torque is maximum because sine is maximum and it is just going to be P. If you talk about the potential energy, this will be the least energy. It will be minus P because theta will be 0, cos 0 is 1. So minus P. Here the potential energy will be 0, but it is not minimum because negative is lesser than 0. And here the potential energy will be maximum and it will be plus P. Equilibrium wise, this is a stable equilibrium. This is unstable equilibrium. And please keep in mind, this is not in equilibrium. Not in equilibrium, because for equilibrium, torque should be 0, force should be 0. And yes, do not forget this fact that whatever force acts on the positive charge acts on the negative charge. So net force is always 0 for a dipole in uniform external field. In uniform field. If the field is non-uniform, then this is usually not 0. So there have been some instances where they might give you a non-uniform field and the force is not 0. Is that clear? Yeah. Okay. Pixel Tech, calm down. Yes, because if you are going to stress yourself, then you will obviously make such simple things as mistakes. Calm down. Don't worry. Don't study too much. Whatever you know, just do it. Just go with the flow. Don't think about the future. Don't think about the past. Just live in the moment, man, right now. Yeah. Okay. Yeah. If you want to divide the wire for finite things, then for finite wire, this is the formula. So I'll just write it over here for a special case. For a finite wire, the formula goes like this. Electric field, if this is not infinite, it will be nothing but 1 by, instead of 2 pi, it is 4 pi epsilon naught. Lambda by r is there. Then you have sine theta 1 plus sine theta 2. Okay, sine theta 1 plus sine theta 2. Here theta 1 and theta 2 are as follows. So if this is your point where you are trying to measure it, see, you just draw a line from the end to the point where you want to measure it. This is theta 1 and this is theta 2. So that's how you can get it. Okay, I hope this is absolutely clear. Then you should know also about the dielectric concepts and their formulas. So the net electric field is always the vector sum of the external electric field and the induced or polarizing electric field. Magnitude wise, the external field is always opposed by the induced field, so it will always oppose it. That is why the net electric field is always going to be than less than your external field. That is how it works. Now that net electric field is always going to be external field divided by K. This is your dielectric constant. Sometimes you also use electrical susceptibility. Okay. Also remember the permittivity in that new medium. Is permittivity which is in vacuum multiplied by that susceptibility or that dielectric constant. These formulas are there for your dielectric mediums. Okay. Next, the concept of capacitance. Remember your capacitance, your concept of capacitance. Yep. This particular C, if this is the positive negative plates charge and there is a voltage difference across it, this Q will be nothing but this capacitance into V, where the capacitance depends on the medium between, not the medium of the plates, medium which is there between the plates. It also depends on the sizes and the dimensions, the sizes and the dimensions, also the shape of those conductors, in all the total geometry, in all the total geometry of that capacitor. The capacitance for a parallel plate capacitor is given by epsilon naught A by D. For a cylindrical capacitor, it is not there, but chumma I'm giving it to you. 2 pi epsilon naught height divided by log of outer radius by inner radius. For a spherical capacitor, like you can see, it depends on the geometry, the shape. Spherical, it is 4 pi epsilon naught 1 by R1 minus 1 by R2. And if it is just an isolated spherical capacitor, it is 4 pi epsilon naught R. These are not there, but chumma I have given it to you. This one is isolated sphere. This is isolated sphere. Isolated sphere. This is a parallel plate capacitor. This one is a cylindrical capacitor. This is just called as spherical capacitor. You should know these basic things. The energy which is stored in a capacitor is given by half CV square, and you should know that when you take a battery, when you take a capacitor connected to a battery, the work done by the battery is basically double of this. So it is just going to be CV square. That means you will have a loss of heat given by half CV square, standard formula. You can also write this potential energy as half Q square by C, or even half charge into voltage, or even half CV square. All these formulas will work. There is no problem with that. Okay, there is no problem with that. If you put a dielectric medium in between, then you just multiply by K everywhere, multiply with K everywhere, if there is some medium which is placed in between the plates of the capacitor. Is that right? Very good. Awesome. Awesome. Then, when the capacitors are in series, when the capacitors are in basically series, it is the charge which is the same, the voltages which are different, which basically add up, to give you the total voltage, and the net capacitance is given by 1 by Cs is 1 by C1 plus 1 by C2 plus 1 by Cn. Same way, when your capacitors are in parallel, when the capacitors are in parallel C1, C2, what is same is the voltage is going to be the same. Voltage is going to be the same, and the charge will be charge on 1 plus charge on 2 plus charge on nth capacitor when we are talking about parallel, and the total capacitance in parallel will be C1 plus C2, like that till Cn. These formulas are there in your books also. All these things you should know. Okay, very good, very good. As you can see, my dear students, these things are there over here. Okay, all these things over here, capacitance in parallel, etc. There is a particular case of interest for parallel plate capacitor. So when you have your parallel plate capacitor, distance between the plates is D, area is A, then there is some electric field in between. The field in between the plates is sigma by epsilon. Sigma is charged by the area of the plate into epsilon. But also remember, there is an attractive force, the force of attraction between the plates, that is very similar to this, but it will be q square by 2a epsilon naught. That factor of half, 1 by 2 will come in the case of force, whereas in the case of field, it will not come. These things you should know. Force of attraction, this is between the plates of that particular capacitor. Sometimes you can be asked to derive this also, and we have done that. Yep. Ritik, very good. You are on your way to the exam center. Glad you're watching this video. Shows the dedication. Shows what the entire India is doing this morning, particularly students of 12th and the parents of 12th standard students. Amazing, amazing. Then let's also move on to the chapter number 3, my dear students. Let's move on to chapter number 3, current electricity. What are the different formulas and other things? Okay. So, in the current electricity chapter, first thing is the current I is nothing but dq by dt, rate of flow of charge, which sometimes you can also say number of charges into each charge divided by the total time. This also works in some situations, particularly where you have to find out how many electrons are moving per unit time, etc. Those kind of questions. When you take the same current and divide it with the area, so the current density is what you get. The current density is what you get, which is current by area, and it's a vector quantity. It's a vector in the direction of that particular current, whose unit is ampere per meter square, just like this was in amperes. Just like this was in amperes. Now, the next concept comes of drift velocity, drift speed, drift speed. That drift speed has many formulas. Electron charge into electric field divided by m into tau. This is nothing but your relaxation time. Relaxation time, the time between the collisions where the electron relaxes when it is not colliding. This is the drift speed. Another alternative formula is current. This particular current which is there, this current which is there, is equal to NVIDIA. NVIDIA. That's it. NVIDIA is the most famous graphics card and now the artificial intelligence company. I is equal to NVIDIA. Yes, you should know this alternative form also. Then you have the Ohm's law. Before we go to Ohm's law, let me also define the resistance formulas. So resistance, R is equal to rho L by A. Rho is resistivity, which depends only on the material. This completely depends on the material. And for a small range, you will see rho is equal to original resistance 1 plus alpha delta T. This is for a small range of temperatures. Alpha is usually positive for conductors. For conductors, it is negative for semiconductors. Negative for semiconductors. Those graphs also we have discussed in the last session. The resistivity decreases for semiconductors. For conductors, it climbs up. Yep, you should know all these things. Also, conductivity, sigma is 1 by resistivity. Reciprocal of resistivity. More resistance is less conductive. Less resistance is more conductive. You should know these things. And now we will go to Ohm's law. Yep. Now we will go to basically Ohm's law. Over here, the voltage is current into resistance. So the voltage is basically that current which is there multiplied by the resistance. This is only true for ohmic devices. Non-ohmic devices like semiconductors, gallium arsenic, right? Most of the other vacuum diodes, etc., they do not obey this Ohm's law. Instead of voltage, you can also divide it with per unit length, and what you get is the electric field. And this current will then become the current density, which we have written over here. And this resistance will become more specific and it will become resistivity. If you want, oh, by the way, electric field is a vector quantity which is having the same direction of current density. You can shift that resistivity on this side. You can shift that particular resistivity on this side. So it will become 1 by rho. 1 by rho is nothing but sigma, which is your current density. This is also another way of writing Ohm's law. There is also a term called as mobility that you get. So that term of mobility, you should know that mobility mu is nothing but how much is your drift speed, how much is your drift speed per unit electric field, per unit electric field. So that is your mobility formula, drift speed per unit electric field. Again, all these things are there over here as well. You can say J is equal to sigma I. I have done it in a much simpler way so that you will never ever find it difficult, or basically you will see things are going to be looking very better. Yeah, correct. Even they have rewritten it in some different forms, like current density, they have written it in relaxation time and electric field form. That is because they have converted sigma, which is your conductivity, as ne square tau by m. So this is another important formula. Sigma conductivity is ne square by m, the whole thing multiplied by tau. So this is the same thing over here. Sigma is also going to be your ne square by m, the same things which were here. This e was there, this m was there, and this tau will come, the relaxation time. Yes, so this is also sigma, which you can put it over here. This sigma you can put it over here, you will still get that. Okay, so all these formulas, if you remember, most of the things are done. Apart from that, resistance in series and parallel are not there, but you know the formulas. For series it is R1 plus R2, for parallel it is 1 by R1 plus 1 by R2. Okay, so that is the main thing. Also, you should know that whenever you get circuits like this, whenever you get a circuit like this is actually three resistors in parallel, three resistors in parallel. Okay, but if you get a circuit like this, a resistor here, a resistor here, or a resistor here, you have one resistor here, one more resistor here. This is the same as this, which is Wheatstone, which is also the same as, which is also the same. This is also the same as one more thing. All these diagrams are equivalent, guys. Yes, all these diagrams, this one, this one, this one, and this one, all of them are Wheatstone. All of them are Wheatstone's arrangement. And to balance it, the balanced condition is that R1 by R2 is basically R3 by R4. What are those resistances over here? This is R1, this is R2, this is R3, this is R4. This is R1, this is R2, this is R3, this is R4. Same thing. This is R1, this is R2, this is R3, this is R4. Same thing over here. This is R1, this is R2, this is R3, this is R4, for example. Actually, over here, this was R3, this was R2. The useless resistance is this R, this particular R over here. or this particular R. This R is completely useless. The current in that resistance is zero. The voltage drop across that resistance is also zero. That means this point and this point are at the same potential. You should know this. Also, from this particular Wheatstone, you have that experiment to measure the unknown resistance. So the concept of your meter bridge concept comes exactly from here. You have your unknown resistance by your known resistance is that balancing length upon 100 centimeters minus L. Assuming L is in centimeters, else things will change. This is in centimeters, this is also in centimeters. This is for your meter bridge. Everyone? Yeah. All right. All right. Very good. Excellent. Keep these things in mind, guys. Awesome. Awesome. So this is there. Yep. All these things. Temperature. Okay. Power formulas. Cells in parallel and in series and Kirchhoff's laws. Okay. So next thing, we'll go to power. Electrical power. Electrical power, guys. Yep. Electrical power is nothing but voltage into current, which is also I squared into R, which is also V squared divided by R. So this is your electrical power formula. I'm just keeping it over here. Now cells in series and parallel, we'll do that also. I'll give you a very easy way to remember it. Whenever you have cells in series, this is E1, R1, this is EN, Rn, the effective combination when you rewrite it as a single resistor and a single EMF, internal. So that single EMF is just E1 plus E2 plus En, and resistance is also R1 plus R2 plus Rn, just like you would do in series. But keep in mind, one of the batteries might be wrongly connected. So there could be plus and minus both, because maybe one of the battery is wrong. So you will put a minus sign in case that battery is wrong. Otherwise, you don't need it. Similarly, when you have cells in parallel like this is R1, this is E1, this is En, this is Rn. So in case of parallel, the resistance formula is very simple, just like resistors in parallel, 1 by R1 plus 1 by R2 plus 1 by Rn. But for the equivalent EMF, look at it, what I will do, put a big line to separate the numerator and the denominator, put E1 by R1, E2 by R2, like that, till whatever nth term by Rn, and below, instead of E1 by R1, just put 1 by R1, 1 by R2, like that, till 1 by Rn. This is going to be much simpler. Much simpler. Empirier, welcome. Yes, Matthew. CBSE students, live in the morning. You wouldn't be asking that question if you had an exam. Okay. Then Kirchhoff's voltage law is the sum of the voltages across a loop is zero. It is based on energy conservation. Kirchhoff's current law based on charge conservation. The total sum of the currents at a point is zero. These two things you should definitely know about. Okay? Kirchhoff's voltage law and Kirchhoff's current law. Where did it go? Somewhere it went. Yeah, Kirchhoff's rules, correct. Junction rule, where when you have multiple points collecting at a point, so multiple wires collecting at a point, sigma I is equal to 0 and sigma delta V is equal to 0. That is the Kirchhoff's voltage law. Okay. Now there is one more thing about the cells which you should know. When there is a battery internal resistance, this is EMF, the voltage difference across it is always E minus IR. If the current is I, this is the terminal voltage. This is the terminal voltage which you should definitely know while it is discharging. While the battery is getting discharged. The battery is getting discharged. So the terminal voltage is slightly lesser than the EMF by IR because there is a drop across the internal resistance. Okay, so let's quickly go to the next chapter over here. Next chapter, moving charges, magnetism, all the important formulas of magnetic field, Ampere's law, inside, outside, solenoid force, and torque on a moving coil, and all these things, the moving coil galvanometer. Quickly. First, let's talk about the Lorentz force. Lorentz force. So that net force acting on a charge, the net force acting on a charge is the sum of two forces. One is the electric component of the force. The second is the magnetic component of the force. The electric component of the force is given like this. You put charge and then you multiply it with the electric field. The magnetic component is given like this. You take the velocity and then cross it with the magnetic field. Now keep this in mind that the magnetic force is going to be always perpendicular to the velocity. Hence, it will not do work. No work will be done by it. It can only change the direction. Nothing else it can do. It can't change the speed. It cannot do work because it is always going to be perpendicular because of this crossed product. Keep this in mind. Similarly, if you have a current carrying wire and let's say there is an element L over here, the current in it is I, and let's say the magnetic field on it is B, then the force acting on that wire, force on the current carrying conductor is given by current into length, but this time you cross it with the magnetic field, IL cross B. This is another important formula for a force on a current carrying wire. But if you have a loop of current, this is a current loop, the moment you take a current loop, then no matter what you do, the net force on it will always be zero, assuming it is on a uniform magnetic field. Yes, there is a uniform magnetic field over here. Then you will see that the net force on that loop, all the forces will add up and they will eventually cancel out each other. The net force on a current carrying loop is always going to be zero. There are two peculiar conditions for this, which you should know. When you take a charged particle of certain mass, throw it with some velocity, it will go in a circular path like this with some radius r, and there is some magnetic field, let's say like this. There is a magnetic field, let's say like this. So that radius is given by mass into velocity divided by qb, and the time period is given by 2 pi m divided by qb. This is particularly independent of velocity. This particular motion is always going to be uniform circular motion. Uniform circular motion. Similarly, if you take that charge and throw it parallel to the magnetic field, then no force will act on it. The force on it will be zero. You can also throw it anti-parallel. So then you will see the velocity will be just like this. It will move in a straight line. Yes, it will move in a straight line without any forces, without any deflection, and this velocity will be constant. But there is another peculiar case where you throw this charged particle making some angle with that magnetic field. Then what it does is goes in a path which looks like this. This is basically a helical path like a spring. That spring like path has a pitch, that is how much you move along the axis. This is also called as the axis of the helix. How much you move along the axis after every revolution, that is given by the horizontal component, which is v cos theta, multiplied by the time period. The time period is the same as before. This is applicable not just for this, but also for this same time period. The radius is also the same, just that instead of v, it is v sine theta. That is the only different part over here. This radius is applicable only for this. This one is applicable for this one, which is mv sine theta component by charge into magnetic field. So that is for this guy. This is for this guy. This is helix, straight line, and circular motion. All the three things you will get. Is that okay, everyone? Awesome. Moving ahead to the next concept. If you have to find the magnetic field for different geometries, you basically make use of Ampere's law, which goes like this. Ampere's law, which goes like this. Integration across a loop of magnetic field with respect to length is the total inside current, or basically you can say enclosed current, multiplied by mu naught. But it gets modified in another chapter, and there is an extra term which comes over here. Which is permittivity, which is basically, sorry, I can put permeability first, and you multiply it with permittivity into d phi by dt of electric flux. This is that extra term that you get. This term which I have written down inside that square bracket, inside that particular square bracket, this term is called as displacement current. Displacement current. Displacement current. This is permittivity. This is rate of change of electric flux. Electric flux, this particular part comes in electromagnetic waves chapter. Yep, correct. Is that right, everyone? Very good. This particular current which is there, this is the actual current. This is also sometimes called as the conduction current. Another important law of of magnetism is Gauss law in magnetism. Gauss in magnetism, and that goes as follows. The total integration of magnetic field with your area is always zero. So the net magnetic flux for a closed surface is zero. This law particularly proves that monopoles do not exist, but only magnetic dipoles are the ones which exist. Also, it says that in a way that the magnetic field lines are always going to be in the form of loops. Magnetic field is always going to be in the form of loops. They will never have a start. They will never have an end also. They will always be in the form of loops. All these things again very important. Then if you take a long wire, carrying some current, and you are standing at a distance r from it, there will be some magnetic field because of it. That magnetic field is given by mu naught I by 2 pi r. Mu naught I by 2 pi r. But if this is infinitely long, wire. If you have a finite wire, keep this in mind. The formula changes little bit. This is your wire carrying current. This is the distance where you are trying to find the field. Here again you do the same thing. Draw the lines joining the endpoints. Mark these angles as theta 1 and theta 2. The only difference is now the magnetic field will be mu naught by 4 pi instead of 2 pi. Current is there, R is there. Here you will have sine theta 1 plus sine theta 2. That's the only difference. That's the only difference. Then the next geometry is if you take a current carrying loop. Okay, if you take a, what is this? This is a current carrying loop. Current carrying loop. Then there are two places where you need to know the magnetic field. One is exactly at the center. Magnetic field exactly at the center is mu naught I by 2 times of the radius. But similarly, if you go at a distance x on the axis, if you go on the axis, then the magnetic field at that axial point is mu naught I by 2 is there. Here you have r square and here you have r square plus x square raised to 3 by 2. That's the big difference. Instead of a current carrying loop, you can also take an arc. The formula comes very, very similar. If you just have an arc which has carried some current, if this is theta, then the magnetic field at the center of that arc, same thing, mu naught I by 2r, but just take a fraction theta by 2 pi. Just multiplied by theta by 2 pi, you will get the answer. Now, when you take multiple such current loops, placed side by side like this, okay, and it continues. Like this. This then basically it becomes a solenoid. What does it become? It becomes a solenoid. And a solenoid has a property called as small n, which is number of turns which are there per unit length, and the magnetic field inside of that solenoid is uniform, and that formula is mu naught, number of turns per unit length into the current, number of turns per unit length into current into mu naught. Please remember outside, so magnetic field outside, it is zero, it is negligible, or it is basically zero outside a solenoid. You take a solenoid and bend it to make it look like this. I know it might not be there or it is there, that's irrelevant. Just imagine this particular diagram where you bend a solenoid so that it basically looks in this shape, like the tube of your tire. This is then called as a toroid. And for a toroid, the magnetic field is only trapped inside that particular toroid. Yes, it is only trapped inside that particular toroid. That formula is also going to be the same, mu naught Ni, which you can also write it as mu naught total turns divided by 2 pi r into current. Here, why 2 pi r? Because the total length is 2 pi r, which is the circumference. 2 pi r is basically the circumference. Is that clear? Very good. Awesome. Now, you also get force between two wires. If you have two wires, which are carrying currents in the opposite direction versus two wires who are carrying currents in the same direction, I1, I2, this is also I1, I2. If they are in the opposite direction, they will repel, very important. If they are in the same direction, they will attract. And this force is given by mu naught I1, I2 divided by 2 pi into D. D is the separation between them. Force between two parallel conductors carrying current, mu naught I1 I2 by 2 pi D. Okay, same direction. Like charges will repel, right? Here it is opposite. Like currents will attract, unlike currents will repel. Exactly opposite of electricity. Correct. You should know this. Very good. Now let's go to the concept of moving coil galvanometer. Moving coil galvanometer. Here you have a term called as theta, which is the deflection. The deflection which occurs in the galvanometer is proportional to the galvanometer current, is proportional to the galvanometer's current. And these constants are very important. You know, basketball, NBA, like you have IPL for cricket, right? EuroLeague for football and all of that, FIFA. Similarly, for basketball, it is NBA, basketball. And in basketball, what should you not do? You should never kick a ball. You should never ever kick a ball. So kick, K. So you should never kick that ball. So number of turns magnetic field into area of the coil, K is your torsional constant. This is torsional constant. Torsional constant. So you can see theta is proportional to I. And then you get this term called as current sensitivity, which is theta by I, which is theta by I, which is nothing but NBA by K. Also, just like you have voltage is current into resistance, here you have sensitivity of voltage is related to sensitivity of current. Do not multiply by R, but resistance comes over here. This is the resistance of the coil. So voltage sensitivity into resistance of the coil is your current sensitivity. This is basically your current sensitivity. This is nothing but your voltage sensitivity. This is the total resistance of your moving coil galvanometer. Keep this in mind. Okay. Next important stuff. If you take this particular galvanometer, it has some coil resistance Rg, but I want to make use of it like a ammeter. So a lot of current will come from outside. You will bypass that particular current through a shunt resistance. This is your shunt resistance. This is also called as your shunt resistance. Most of the current will go from here only. So this will be I minus your Ig. Ig is usually, Ig is your usual full scale deflection, maximum deflection which can occur in the current, deflection current. This capital I is usually the range of that particular ammeter. So this particular box with the shunt resistance and the galvanometer together is sold as an ammeter. Ammeter is always connected in series with the circuit, and an ideal ammeter will have 0 ohm resistance. It should have negligible resistance because it is connected in series. As you can see, everything is in parallel and the currents are getting divided. The voltages will be the same. The voltage across the galvanometer will be voltage across the shunt. Voltage across the galvanometer is Ig into Rg. Voltage across the shunt will be nothing but I minus Ig, that's the current, into the resistance. This is the formula which you should remember. You can rearrange it and get whatever you want. Please don't by heart any other thing. It's just that these two are equal because they are in parallel resistance. In parallel resistance, voltage is same. Parallel resistances, the voltages are same. The potential drop is going to be the same. If you remember that, it becomes very, very easy to solve the problem. Similarly, when you have a galvanometer with with coil resistance Rg. You connect it in series with a very high resistance R. And now you measure the total voltage drop across it. The maximum current which can go is again Ig, is basically Ig, which is your full scale deflection current, full scale deflection current. And the maximum voltage that you can measure is V, which is the range of that particular voltmeter. This particular device with the galvanometer and the series resistance, this is then called as your voltmeter. Voltmeter is always connected in parallel with your circuit. And if you have an ideal voltmeter, it has infinite, resistance. Because they are in series, I can immediately say that the total voltage is that current which is there, which is basically your Ig, multiplied by the total resistance, which is Rg, which is basically Rg plus that series resistance, which is R. So that's it. That's the formula. V is equal to IR. Resistor in series, you just add them. So basically both of them are in series. So that is the reason why you have added them, and the current through them is the same. In ammeter, the resistors are in parallel. Is that clear? Yes, Bala, your captain is online. Awesome. Very good. Very good. Excellent. So these are the things in your magnetism which you should know. All right. Then here, magnetism and matter, more or less a theoretical chapter. Not much is there, guys, except for again similar formulas are there. Electrical, magnetism, analog, and all these formulas. There is not much of formulas except for few things here. Magnetic properties are given, susceptibility, etc. I'll just brief you about it. See, if you have a coil carrying current, coil, this is, let's say, current, this is your coil carrying current, and you have your permanent magnet. They can be compared with each other. This is North Pole, this is South Pole. These two are comparable with each other because this current carrying coil also produces a North Pole and a South Pole, and it has its something called as magnetic moment. So even this has its own magnetic moment. This magnetic moment is given by number of turns into current into area, just like you had electrical dipole moment. Same way, for a bar magnet, the magnetic moment is given by, you take the magnetic charge Qm. This is your magnetic charge, how much magnetic pole strength is there, magnetic charge, or sometimes called as the strength, pole strength, either of them, multiplied by the separation, multiplied by the L is nothing but the separation between them. Both of them are basically the same things. Both of them are basically the same things. So when you take either of these bar magnets or this current carrying coil and you place this in a external field, you place it in an external field, then M cross B, just like before, and minus M dot B, just like before for electricity, this will give you the torque acting on it, and this particular thing will give you the potential energy. This will give you the potential energy. Just like in electricity, just like in electrical dipole, there is no difference at all. Even the field and potential due to the dipole formulas are same. Yes. So if you take a magnetic moment or a magnetic dipole and somebody decides that, okay, I'm going to go on the axis, then what is the magnetic field on the axis? The formula is mu naught by 4 pi magnetic moment by r cube. into 2. Similarly, if one decides, okay, I will go on the equator, so the magnetic field on the equator is mu naught by 4 pi m by r cube. M by r cube, that 2 is not there. Same thing for magnetic potential and everything, guys. So here the magnetic potential is mu naught by 4 pi. In general, you can use cos theta, m by r square cos theta at any general location. At any general location, same formulas are applicable, guys. There is no difference at all. There is no difference at all. Okay, all these things you should definitely know. You also get this term called as gyromagnetic ratio. Gyromagnetic ratio is where you have some charge, and it is revolving. Because it is revolving, at some angular velocity and that particular radius, you will see it will develop some angular momentum. It also has some magnetic moment. Yes, over here, the magnetic moment, which will be north pole, this will be south pole, so the magnetic moment will be like this. So the magnetic moment divided by L, which is the angular momentum. This formula, what is L over here? This is your angular momentum. Angular momentum. M is magnetic moment, is nothing but the charge divided by 2 times the mass. Charge divided by 2 times the mass. This is called as the gyromagnetic ratio of rotating charged bodies or revolving charged bodies. You should know that. Is that okay? All things very, very important, my dear warriors. So that is what is there over here. Apart from that, you can just have some basic formulas like, relative permeability is permeability of that particular medium divided by permeability of that free space, and relative permeability is 1 plus susceptibility. This is your susceptibility. Yeah. Then you also have terms like magnetizing field, H, which is nothing but your external field divided by mu naught. Then you have magnetization. By the way, this is a vector quantity. That symbol is I. Magnetization is how much field is being induced divided by mu naught. This is also a vector quantity, which can also be written down as, the total magnetic moment divided by unit volume. This is total magnetic moment. The total magnetic moment divided by mu naught. This is also very important. This susceptibility can also be written down as I by H. Very, very important. I divided by H is also susceptibility. You should know the 3 different things. Diamagnetism, then you have paramagnetism, and then of course you have ferromagnetism. For diamagnetic materials, the susceptibility is negative and the relative permeability is less than 1. Okay, and they repel the magnetic field. Whereas paramagnetic, it is a small positive number. The relative permeability is more than 1. They attract weakly. Weak attraction is there with the magnetic field. Ferromagnetic material, the susceptibility is too much positive. The relative permeability is much, much larger than 1, and they have strong attraction. So this is for your ferro. This is for your ferromagnetic materials. These basic things you should know. Yes, very good, excellent. Awesome. Then let's go to the Next part, quickly, guys. Magnetism and matter done. Okay. EMI, basic formulas are there. In electromagnetic induction, you have your Faraday's law, which just says that the EMF is minus d phi by dt, but this is magnetic flux. And this negative sign which is there, it comes because of Lenz's law. Lenz law gives you the direction. Lenz's law, which gives you the direction based on the energy conservation. It is based on energy conservation. Very good. Then next is motional EMF. Motional EMF formulas. So if you take a rod of certain length, move it with some velocity in some magnetic field, then the EMF developed is given by LV into B. The direction is given by V cross B, which is also your Fleming's right hand rule. This is your Fleming's right hand rule. Just do V cross B. That will be the direction. Velocity is here, magnetic field is inside, it is going like that. So this will be the positive, this will be the negative terminal when you do V cross B. So the current will be going like this. So the current will be going like this. Here, because EMF is known, you can also find the current in that coil, which is EMF divided by the resistance. That is another thing which can be used at times. Okay. Then you have the formula for inductance. Inductance. Yep. So the magnetic flux which is produced within the coil, is proportional to the current. That constant is called self-inductance. Self-inductance. And the EMF developed in that same coil is minus L, derivative of the current with respect to time. The energy stored in that field is half epsilon naught E square. Sorry, my bad. Half L I square. This is the energy which is stored in that field. This is that energy which is stored in that particular field. And if you take a solenoid, if you just take a solenoid, if you take a solenoid, the inductance of a solenoid is mu naught, number of turns per unit length square, into area into the length. This is the formula, mu naught n square AL. Yep, mu naught n square AL, correct. Yeah. But if you take one solenoid inside the other, then what you get is the mutual inductance. These are basically concentric solenoids. You get mutual inductance, which is mu naught n1 n2 area into length, area of cross section into length. And just like before, the flux in the secondary coil is proportional to the current in the first coil. This coefficient is called the coefficient of mutual inductance. This is your mutual inductance. Very, very important. Again, is that clear, everyone? Very good, very good. Series and parallel are very, very similar, guys. So whenever you have inductors connected in series, the effective inductance is L1 plus L2, like that till Ln. And if the inductors are basically in parallel, so if they are in parallel, then use the same formula like in parallel for resistance, 1 by L1 plus 1 by L2, like that till 1 by Ln. That is the formula. There is no difference at all. Yep, there is no difference at all. Okay. Anything else that we have missed in inductors? I doubt. In EMI. AC generator is there. Okay. So AC generator, AC generator, AC generator, that EMF which is produced, this is the voltage AC voltage which is generated, is given by magnetic field into area of coil into angular velocity into number of turns into sine omega t. So this clearly tells me, this sine function clearly tells me the voltages will be varying like this, just like a AC should. Born sine omega t, that is the formula. You should remember this. Very, very important formula. Correct. Let's go ahead, guys. Let's go ahead. In ray optics, what are the main formulas? Let's go with that. See, I will put mirrors on one side. I will put mirrors on one side and I will put lens on the other side. Okay, I will put lens on the other side and you will see there is a lot of similarity and difference also. For example, when you try to find the focal length of a mirror, focal length is r by 2, but in case of lens, it is 1 by f is equal to refractive index of the lens with respect to the medium minus 1, and then you have 1 by r1 minus 1 by r2. That is the lens maker formula. Here it is 1 by v plus 1 by u is equal to 1 by f. Here it is 1 by v minus 1 by u is equal to 1 by f. The magnification is v by u. Here the magnification is minus v by u. Here the power is 1 by f with a negative sign. Here the power is just 1 by f. That is the main difference between mirrors and lenses, formulas wise. Okay, very important. Is that right? Okay, great. Now, don't worry, we'll come to AC. I have not skipped AC. Bro, I have not skipped AC. Chill, Anush. Okay, hold on. Hold on, I'll come to that also. Just hold on. Okay, next important thing, if you have curved surface and plane surface. So plane surface refraction, whatever formulas are there, let's quickly recollect them. First is N1 sine I is equal to N2 sine R, that is your Snell's law. Then you also have sine of I by sine of R, which is also called refractive index, which is N2 by N1, which if you want, you can also write it as N, light has gone from 1 to 2. This is also speed of light in the first medium upon speed of light in the second medium, which is also lambda 1 by lambda 2. Because the frequency is the same, it gets cancelled out. The frequency will get cancelled out. Speed of light is frequency into wavelength, so I'm just cancelling out the frequency. Then you have the concept of apparent depth or apparent height. So apparent depth, when you are looking inside water, will be the actual depth upon refractive index of that particular fluid, whereas apparent height, that means you are inside water and you are looking at things outside in the air, is the actual height multiplied by the refractive index. These concepts are there over here. You can also find the angle of deviation. The angle of deviation is I minus R in case of refraction. I minus R in case of refraction. Similarly, you have curved surface refraction, curved surface refraction, my dear warriors. So the curved surface refraction formula is as follows: mu2 by v minus mu1 by u is mu2 minus mu1 divided by the radius of curvature. Mu2, mu1 are the refractive indices of the mediums which are separating that particular surface. That surface has a curved nature, that is the radius of curvature. Then we'll talk about prism formulas. What are the formulas in prism, guys? First, angle of prism is internal angles R1 plus R2. The total deviation is I plus E minus A, correct? Then you can also say sine of I by sine of internal angle is sine of E divided by sine of that internal angle, which is refractive index. But when you go to a more specific case of minimum deviation, minimum deviation, then you will notice few more things like I is equal to E, R1 is equal to R2, and you will see that refractive index is sine of A plus delta minimum by 2 divided by sine of A by 2. These are the formulas. When you talk about thin prism, when you talk about thin prism, my dear warriors, then the deviation is given by A into mu minus 1 directly. A into mu minus 1. Thin prism means angle of the prism is very, very small. Graphs I have completed yesterday only. If you want, I will keep the graphs here. Oops, where is it? Yeah, here. I've kept all the graphs here, guys. All the graphs which I've discussed yesterday, I've kept it here. I'll be sharing the notes on Telegram, by the way. If you're wondering where is Shreyas sir going to share the notes, Shreyas sir is going to share the notes on Telegram. Are you a part of Telegram? No. Very good. Congratulations. If you're not a part of Telegram, be a part of the Telegram. Sir, where do I join the Telegram group, sir? Yes, it is here. Where do you go? Go down over here. It's there. It's there. It's there. It's there. It's there. It's there. Yeah, the Telegram groups. The Telegram groups is over here. Join us on the Telegram, WhatsApp, Instagram, everything is there. So just click on this. You will be joining the Telegram group. Is that okay? Vedantu JEE English. All right. Perfect. Then our optical instruments. Optical instruments. I have already shown you the ray diagrams before. I've already shown you the ray diagrams before. So I will just directly head over to that particular part. Ray diagram, ray diagram. Yeah, over here. So if you talk about magnifying power, the magnifying power is D by F if it is normal vision, normal vision. But the same magnifying power becomes 1 plus D by F if it is least distance of distinct vision. When you are holding the objects as that, the image is formed at least distance of distinct vision. For microscope, the magnifying power is the magnification of the objective lens. So it is basically, clear this out. Okay. Magnification of the objective lens. Magnification of the objective lens means just V by U. Always take the mod values. Always take the mod values. Multiply it with the magnification of the magnifying power of the eyepiece. Magnifying power of the eyepiece. It is just going to behave like a simple microscope. So it can be either D by F or it can be 1 plus D by F, depending on whether it is normal vision or least distance of distinct vision. Depending on that, this will change. So this in total will give you the total magnifying power of that. Now, usually what happens that the image distance for a simple microscope becomes the length. Sometimes this approximately becomes the image distance becomes the length of the tube because the image is formed very close over here, and the object distance becomes the focal length of the objective. So usually it becomes L by FO. And by the way, this focal length over here is the focal length of the eyepiece. This is only sometimes when that approximation is valid. Otherwise, use V by U. Otherwise, use V by U formula. Is that okay? Here, come on, let's see how many of you remember the magnifying power of the telescope. Come on. And also the length of the tube. Length of the tube. FE plus FO. Focal length of the eyepiece plus focal length of the objective. Yep. Yes. What about the magnifying power of the telescope? NCERT diagram is very similar, bacha, my dear. I'm so glad, Good Lynch, it is boosting all of you. Yes, this is your last physics exam, hopefully. Yes. Yes, you should know that magnifying power, focal length of objective and focal length of eyepiece. You should know these things. Telescope. Okay. So that is about telescope. Okay. So last few chapters remaining, guys. Let's go ahead quickly. Let's go to AC now. Ready? Where is that AC fellow? Where is that AC fellow with that skull? AC. Let's do AC also. Okay, great. See, I'll tell you, AC is simple way to do things. In series LCR, in series LCR circuit, it is the current which is the same. It is the current which is the same, and the total voltage which is there, the total voltage which is there adds up like vectors. Voltage across the resistance plus voltage across the inductance plus voltage across the capacitance. So it is basically the vector addition of the phasors. This is very, very important. Current is the same. Voltages add like vectors because they are phasor quantities. Okay, great. Magnification is minus V by U. Did I not give that? Oh, sorry. See, silly mistake I did. So sorry, guys. Thank you for pointing it out. My bad. Please correct this, guys. This was minus V by U and this was plus V by U. So sorry. Yeah, just correcting it. Just correcting it. Thank you so much for pointing it out. Yep. Okay, going to AC. Okay, so first thing first, if you show the current phasor horizontally, resistor always aligns with it. The phasor of resistance is always with it. Inductor and capacitor, who is on the top, who is below. Love is above all. Love for inductance. L for inductance, L for love. Yes. So VL will be on the top naturally. VC will be below. And the vector sum of these three vectors is going to be your total voltage, which will have some phase angle, phase difference. Now, this expression tells me the scalar value of V instead of the vector will be root of so many things. Base is VR plus the height of this will be VL minus VC. So it will be VL minus VC whole square using Pythagoras theorem. You can do the same thing with, even the resistances. Yes, with the resistances also. The resistance is always in phase with the current. The inductor's resistance is always on the top. The capacitor's resistance, which is called reactance, is always below. So from this, you can see who leads whom, who is behind whom. Oh, by the way, omega is always like this. Omega is like this. So if you ever wanted to see who is behind, who is ahead, voltage is ahead of current for inductor, current is ahead of voltage for capacitor, because they go right like this, anti-clockwise. Yeah. Now this XL is nothing but omega into L, capacitive and inductive reactances. This is capacitive reactance will be 1 by omega C, and the net resistance is then called impedance, which is Z. This is again same phi. This Z is just then the root of R square plus, this is the base, this is the height is XL minus XC. So XL minus XZ whole square. That's how it is. Also notice one interesting thing. Okay. Resistance XL, XC. Okay. Current is the same. I. Okay. This is the total impedance. Current into resistance is voltage. IR will be VR. This will be VL. This will be VC. And this as a whole will be nothing but the total voltage. So just like you had Ohm's law, even this is valid. Here you can see from this particular diagram, tan phi can be written down as VL minus VC divided by R, and cos phi can be written down as adjacent side, which is VR divided by total voltage. Same thing, you don't have to remember this. Cos phi over here will be R by Z, but if you want to write tan of phi, that will be XL minus XC upon basically R. So these are things which come naturally by trigonometry. Last thing over here is the power formula. Last thing over here is basically the power in this particular thing. So the power is, remember, always IRMS, not any current, IRMS square into the resistance, which can be also written down as VRMS, the total voltage, VRMS square, oh, VRMS, IRMS, and finally multiply it with cos of phi. This is also called as the power factor. Keep this in mind. Important condition, in resonance, keep this in mind. XL is equal to XC. That also means the total impedance is the resistance. Voltage across inductor is voltage across capacitor. That also means the total voltage is the voltage across the resistance. Cos phi is 1. That also means the phase angle is 0 degree and the current is maximum, and it is the total voltage by the resistance. This is during the phenomena of resonance. This is your complete AC chapter in one slide. Is this amazing, guys? Did you love this diagram? Yeah, over here, these are all the magnitudes. This is not XL minus XC exactly. It is the magnitude. So this also VL minus VC magnitude, mod value. Did you love this slide? Everything is there, guys. This is like your cheat code. Please don't carry it in the exam hall. Yeah, please don't carry it in the exam hall. Okay, last things. Now we have come to, what do you say? See, in waves, there is only one formula majorly which you need to remember, that is fringe width, lambda d by d, for constructive interference n lambda, or destructive interference odd lambda by 2, and that single slit diffraction formula. So other than that, it is mainly theory, lot of theory is there, not many formulas. You can just go through it. I'll come to modern physics quickly. So in modern physics, first let's go to photons and photoelectric effect. First, the energy of a photon is h into frequency, which is also hc by lambda. The momentum, this is momentum of a photon is h by lambda, which is also h e by c, energy of that particular photon by c. The intensity of the photon beam is number of photons into energy of each photon per unit time, and this is per unit area. This is the intensity formula, which again you should know. Then what else is there? Yeah, then the photoelectric equation, which is energy of the photon is the work function plus the maximum kinetic energy. The energy of the photon, we already know, either I can use hf or you can use hc by lambda. Work function, you can use hf naught or you can use hc by lambda naught. These are threshold frequencies and wavelength. Maximum kinetic energy, you can also write it as E into stopping potential. This is your stopping potential, guys. Stopping potential. Everybody remembers this? Yes, very good. Similarly, you have the dual nature concept. Dual nature. So when a particle possesses momentum, the de Broglie wavelength is h by p, where p is nothing but mv, which can be also written down as root of 2m into kinetic energy, which sometimes can be also written down as 2 times m times charge into voltage difference. All these things are the same. The total energy of the particle is half m velocity square. Half m velocity square, which you cannot write it over here. Remember, the mass of a photon at rest is assumed to be 0, which is not true for a particle. It can move with any speed, it can have any mass, but a photon has to travel at the speed of light. That brings me to also electromagnetic waves concept, where you have electric field wave equation given by E naught sine kx plus or minus omega t. This k is 2 pi by lambda. This omega is 2 pi into frequency. This is the amplitude of that particular wave. Same thing over here, magnetic field equation is B naught, which is again the amplitude, sine kx, k is the same thing, plus minus omega into t. Omega is again 2 pi f. When do you use plus? When do you use minus? Plus is when the wave is going along negative x-axis, and you use minus when it is going along positive x-axis. So it is exactly opposite. The speed of light is 1 by permeability into permittivity of free space, which is also E by B, which is also E naught by B naught, which can be also written down as speed of light in vacuum upon refractive index. Refractive index. This is also going to be fine, guys. This is also going to be fine. Okay, all these formulas are valid. Even I can write this as C is equal to F into lambda, or also omega by K. So the same K and same omega, same wavelength and same frequency. K is called angular wave number. This is angular frequency. Angular frequency, angular wave number. Next thing which you should know is that the density of electrical energy is given by half epsilon naught E square. This is RMS field. And similarly, the density of magnetic field energy is half epsilon naught magnetic field RMS square. And these both are present in equal amounts. They are present in equal amounts in a electromagnetic wave. Keep these things in mind. Yes, keep these things in mind. The radiation pressure formula, the radiation pressure formula, that radiation pressure is intensity by C. The radiation force is IA by C. I is intensity, A is area, A is basically area, and C is the speed of light. So the force exerted by electromagnetic wave on a surface is given by this radiation pressure and radiation force. You should know these things. Okay. Wave. I'm so glad KS Wali. Okay. Dual nature also done. This last formulas now. Last formulas. Atomic structure. Atomic structure. Atomic structure. First thing, Bohr's laws postulates. First law postulate says that the electric force is given by mass into centripetal acceleration, which is v square by r, and this is nothing but 1 by 4 pi epsilon naught charge 1 charge 2 divided by r square. The second law says angular momentum is integral multiple of h by 2 pi. This is nothing but mass into velocity into r. And the third Bohr's law says that the energy difference between the orbits E2 minus E1, whatever is there, is going to be the energy of that photon, which is nothing but hf, which you can also say is hc by lambda. So these are the three postulates. From this you get the equations like the radius is r naught n square by z. Yeah, radius is proportional to n square. Then the velocity is basically some original velocity in the first orbit into z by n, and that total energy is minus 13.6 z square by n square. That is the formula. This energy is the sum of kinetic energy and potential energy. If you measure the kinetic energy, it will be just the negative of the total energy. The potential energy will be twice of the total energy, 2 times of the total energy. This is again something which you should be aware of. All right, everyone. Now, this particular thing, because when energy is released or absorbed by a photon, the difference of the energy gives me the wavelength. That gives me to the Rydberg's constant formula for electron transitions, sorry. 1 by lambda is Rydberg's constant Z square, 1 by N1 square minus 1 by N2 square. This is something which you should again definitely know. Is that clear? Yes. Okay. Last thing for nucleus, my dear students. For nucleus, the radius of the nucleus is R0. Atomic mass number raised to 1 by 3. Atomic mass number is number of protons plus neutrons. This is the number of protons. This is the number of neutrons. And remember, this is atomic mass number. Okay, keep this in mind. Then you have energy which is created or destroyed is mass defect into c square, which you can also write delta m, provided this is in atomic mass unit. You multiply it with the number 931, you get the total answer in mega electron volt. That is the binding energy which you get. That is the binding energy, binding energy that you get. Also remember, the binding energy divided by A gives me the stability of the nucleus, stability of that nucleus. Now, delta M, which is the mass defect is always the mass which you are expecting, what you are expecting minus what you actually get. So see which is bigger, which is smaller. Accordingly, take the bigger number minus smaller number. Don't be a fool, okay, to make these silly mistakes. Sometimes you can also use the same formula for Q value. The Q value of your fission or for your fusion reaction, that formula is also very similar. Delta M into 931 mega electron volt. There is no new formula over there. Okay, so all these are basic things over here. Apart from that, what is that? Z is atomic number, protons, which is also atomic number. This is atomic number. This is atomic mass number. This is atomic mass number. Okay, great. Okay, great. So I think we are done. All right. Now I just want to tell all of you a big all the best, my dear students. Now this is not the end. Obviously, we have lot of exams to conquer. JEE, all right. Other competitive exams. Okay. Obviously, we have advanced so many other things. Everything only on JEE English. Only on your JEE English. Yep. Which is obviously your #1 English channel in the country. I feel you will do awesome. Whatever I have done, if you want, play it in a loop as you are traveling, or if you are taking rest, just listen to whatever I have said in a loop in 2x speed, 4x speed, up to you. Okay. Don't study 1-2 hours before the exam. It will unnecessarily cause stress. Talk to your family members, lighten the mood. Don't look into the eye of any other friend. Don't call up anyone. Just relax. Eat decently. Don't eat too much. Go to the toilet. Clear up all your things. Don't have to go to the toilet in the examination. Drink decent amount of water. Keep yourself hydrated. If you are sweating too much, see if you can carry some tissues or handkerchief. Give rest to your hand. Do some hand exercise. Move your head, or else sometimes the head gets jammed. Okay. And also read all the questions properly. Don't think you know the question or you have solved it before. They might have changed a word in the examination paper. So please read it carefully. Select questions carefully. Don't try to be a hero. Where you know that you will get more marks, write that question. If you feel that there are two questions where you don't know completely, then don't solve both the questions. It is a waste of time. The examiner will not select where you will get higher marks. No, that is not the job of the examiner. He will see whichever is first, he will give the marks. He will not even check the next question. Okay, keep this in mind. So please select that question where you know more marks. If you do not know the entire question, at least write the given, at least write the formula, at least draw the diagram. If you can substitute even the wrong values, substitute it. Or if you know the values are correct, but I don't know how to proceed with the next step, substitute something, find something, do something, get something. Just get something. Just if they are asked what is the force or what is the EMF, find that EMF, find a wrong value, it's okay. Just get something, man. Don't leave it blank. Please, for God's sake, man, don't leave it blank. Okay? Just write something. Let them feel, oh, you have tried something. They won't have so much time to check the paper properly sometimes. Okay? So, semiconductors, there are not much formulas. Okay? It's just diagrams and theory. So, no point revising it right now. So, please join the Telegram group. I'll be sharing it right now. And if you have not yet liked the video, what are you guys doing? I mean, come on, guys. I woke up for you in the morning. So, quickly make this 1K likes. Immediately share this video with all your friends and they too can revise. Okay. Thank you so much. All the very best. Subscribe to the channel. Lot of sessions coming for you for chemistry, maths, and of course, after that for JEE Mains, JEE Advanced, BITS NIT, VIT EEE, SRM, JEE, you name it, guys. Okay. All the best. Have a great time. See you very soon on the other side. Yeah. Do well.